Good evening. We will now be beginning a new unit, and this one will now look at electricity and moving on further towards magnetism. Right now, we're going to begin with electric forces and charge and how it builds up, etc., etc. So tonight's lecture follows along in section 8.18, chapter 18, sections 1, 2, and we'll jump up onto section 5. All right? Thank you very much. Follow along here, and let's get to it. We're all charged up. Electric charge is a fundamental property of the building blocks of an atom. And it contains, so within an atom you have the proton, the electron, and the neutron. The neutron has no charge, it's neutral. The proton is positive charge, it has a +1 charge. The electron has a negative charge, a -1. We can only go up in charge at a integer value. It's kind of it's what we could say quantized. So you can only have you never have like electrons with 1.5 negative charge. It's only like you have -1, -2, -3, etc. up there. We do denote that the unit of electric charge is Coulomb, and we say that one electron, individually one electron, a single electron, has the charge of the magnitude of that is 1.6 times 10 to the -19 coulombs. So it's a very tiny, tiny, tiny amount of charge on an electron or on a proton. And the difference between the masses of the proton and electron are very great, whereas they have an equal but opposite charge. So charge is really just a fundamental property within these protons, electrons, and there's more and more quantum physics getting up to what's behind that, and behind each one of those we're a little concerned with what comes next down the line. But from this we get the idea that this idea of the charge for each of these elementary particles. So we talked about the neutron having no charge, and that just means it has no net charge. It will not interfere or influence or have any interaction between a proton and electron in a purely charge specific way. There is a force of attraction. There are other forces that are playing here, but we're going to, in the force of the electrostatic force, in this concern, there is no other value there is no thing that we're concerned about for something there. The charge of an electron and a proton, again, smallest amount. They can only go up by an integer value, that n value. So you can never have like 1.5 electrons worth of charge. You really only say you have a quantized amount. So you could have 1, 2, 3, 4, etc. moving up for some value of charge on within a atom or molecule. When we look at atoms individually, and not atom wolves, but atoms as in the elements, and hopefully you are familiar with the idea that the proton and the neutron are located in the center of the atom, and the electron is in some sort of cloud. It's anything going around the outside. Now, when we get to Heisenberg's uncertainty principle, we can never know both the speed and the position of the electron. We can only know one of the two. But anyways, that's neither here nor there. So the idea that you never really add or remove protons from an atom, you either add or remove electrons. This is a main thing here. So you can either add negative charge to make something have a negative net charge, or you can remove negative charge, removing electrons, to make something have a positive net charge, to make some object there. You can never add or take away protons. You can only add or take away electrons. The other idea is that there's always the conservation of charges within a set system, so that the total amount of charge does not ever change. And pretty basically, and I'm pretty sure you're familiar with this, opposites attract and similar things repel. So a positive and a negative, they attract towards each other, and a negative and a positive attract towards each other, and two negatives repel each other, and two positives repel each other. This is because when two charges interact, they apply a force to one another. And this is known as what we'll talk about in a second, Coulombs law. But they apply this force, and it's either an attraction or a repulsion. So it's important to notice whether or not the charges are similar, positive, positive, negative, negative, and whether they're opposite, and that will tell you whether the force is attractive or repulsive. Coulomb's law, it comes from a formula or a way of describing the electric force or the electrostatic force between two charges. The force depends on the electric constant, which in itself actually depends on the permittivity of free space, which we'll talk about a little bit more later on, and we'll get to that later, a couple more weeks down the road. I was trying to go through my head when it would be. But the main idea that I want you to understand from this is that the electric constant is equal to 8.99 times 10 to the 9th Newton meters per Coulomb squared, and that's meters squared also. It also depends on charge 1 and charge 2. Now, if the force ends up being positive overall, that means that it is an attractive force, and if it's negative overall, that means the force between the two charges is repulsive. They're pushing away from each other. It also depends on the distance between the two objects, or between the two charges. Now, we've seen a formula very similar to this, following the same idea of this inverse square law. So as you increase the distance, et cetera, the force actually decreases as a square of the distance, but that's what the idea of this inverse square law. Here, this is very similar to the universal law of gravitation, which we've seen before. So, excellent. Here we go. This is the force, Coulomb's law. We're going to get to love it. It's going to be great. Excellent. All right, tonight's question pertains to Coulomb's law, and we're only going to really look at Coulomb's law for this. And I want to know how each of the following changes would affect the electric force, or electrostatic force, between two point charges. Let's say you double the charge of Q1. What happens to the force? Now, let's say you double the distance between the two charges, charge 1 and charge 2. What happens to the force? Let's say you triple the amount of charge for each, for both actually, and really like thinking about it that way, of charge 1 and charge 2. And finally, let's say you triple the distance between charge 1 and charge 2, and at the same time triple the charge of each of both of the charges, Q1, Q2. What would happen to the force? Thank you very much. Have a great night. Enjoy the video, and please follow along in the textbook, because it really, this is a whole new section that we're getting into, and it's really important to come in with some questions and make sure you have fully read through the textbook, because there is other aspects there that are not covered in this video.